In today's video, we're going to be looking at circuits once again. And after watching this video, you should be able to distinguish the difference between a parallel circuit and a series circuit, and then understand some of the drawbacks and benefits of each type of circuits. So this is just basically an introductory look at the two different types of circuits, and then in the next two lessons, I'm going to kind of focus in on parallel and series circuits, each having their own video. So let's start right away and take a gander at the two different types of circuits that we'll be talking about in this class. The first type of circuit is called a series circuit. Okay, series circuit. And basically, all the parts of the circuit are along a straight line or path. Now, I don't want you to think that it has to be in a straight line so much, but basically it's that they all must follow the same path. And when I say they all, the charges must all follow the same path. So the current has only one possible way to go, and there is no other option for it. And basically, throughout the circuit, the current stays constant. Okay, and that is one difference from a series circuit to the other type, which is called a parallel circuit. Okay, that the current does stay constant throughout the entire series circuit. Okay. A typical example would be Christmas lights. Okay, if any of you guys, now the newer ones, this is not so true, but if you have an old pair of Christmas lights, you're probably looking at a series circuit, and the reason why I'm saying that is because if one of the light bulbs is burnt out in that string of Christmas lights, the whole string is broken. You need to figure out which bulb's not working, and then once you get that bulb fixed, then the string will work. Now, newer versions of Christmas lights, that's not so much the case. They have since fixed that and turned those into a parallel circuit where if one bulb goes out, the whole string doesn't go out. But this was a good example back in the day. The second type of circuit is called a parallel circuit, and basically the current in a parallel circuit has choices. It has multiple paths in which it can travel through the circuit. The current will follow the path of least resistance. All right, so basically what this means is the current is not the same everywhere, which if you remember, can't write and talk at the same time. The same everywhere. And if you remember from the previous slide, this is different than what a series circuit was, where the current was the same everywhere. In a parallel circuit, it's not. But one thing that is interesting is all the branches of a parallel circuit will have the same potential difference, the same voltage, okay? Which when I start to show some pictures, this will make maybe a little bit more sense. But an example of this would be your house. The wiring in your house is without a doubt a parallel circuit. All right, and the reason why I'm telling you that is, let's say you have something like not working. Let's say you like your light bulb in your lamp blows up, not blows up, but like blows its fuse or whatever, and it's no longer functioning. Well, if that lamp is on the same circuit as, say, your refrigerator, now your refrigerator doesn't work because there's a break in the circuit. If it was a series circuit, now it's not, because basically your lamp cannot work, but clearly your refrigerator still keeps on running, and so they make home wiring be a parallel circuit. Okay. The other thing that would show up if it was a series circuit was that basically as you add more and more devices to the circuit, you would notice less and less power. So all your lamps would get lower and lower in terms of brightness. As you add another lamp to the circuit, it'd be kind of weird. Your lamps would get dimmer and dimmer because there'd be less voltage for each of those devices that you add to the circuit. So that's why they don't wire houses in series. Instead, they wire them in parallel. So here are some more properties of a series circuit. As more resistors are added to the overall current within this, as more resistors are added, the overall current within the circuit decreases, and that kind of makes sense. As you add more devices to the circuit, there's going to be less current passing through it, or it's going to slow down, okay? And as I've been kind of mentioning in the previous slide, if a bulb in a series circuit is unscrewed from its socket, then the other bulbs will immediately go out because the circuit is now broken. And this was the biggest pain with Christmas lights. I can still remember to this day when we'd be trying to string Christmas lights on a Christmas tree, one of the bulbs would not be working and the whole string was broken, and you'd have to try to figure out which bulb was not functioning correctly. Some properties of a parallel circuit would include, for parallel circuits, as the number of resistors increases, increases, the overall current also increases. And this throws a lot of students through a loop, because if you actually read that and think about it, that sounds like it doesn't make sense. If you add more resistors, the current increases. How can that be? Well, don't worry, I'm going to show you a picture and this will maybe make more sense. If an individual bulb is unscrewed from its socket, the other bulbs still work with a parallel circuit. And so this is why we wire our homes this way, because we don't deal with these issues of one bulb not working and then like a whole chunk of your house does not have power. Adding more, so this is just kind of a summary of the previous two slides. Adding more resistors in series means that there is more overall resistance, Yet adding more resistors in parallel means that there is less overall resistance. And this, to me, at first, when you read it, does not make sense. But I think when we go back to my skier analogy, this will make a lot of sense in just a second. So I'm going to explain this guy right here with a picture. Fear not. Okay, so I've been talking about circuits kind of like if you were to go to a ski resort and, you know, ride up the ski lift, get up to the top of the hill, go down the hill, and then repeat the pattern, okay? And I've been saying this entire time that the ski lift could be represented as a battery, okay? And if you remember in the previous lesson, we learned that this is the symbol for a battery. If I were to draw a series circuit, it would look something like this. As the skiers travel around the course and head back to the battery, if I were to say throw a resistor right here, okay, what would that do to the skiers as they travel through this circuit? And I'm hoping you're thinking it would slow down. And just to kind of make it maybe a little bit more understandable, let's pretend these resistors, the resistors equal hot chocolate stands. Okay, because I don't know about you, but there's nothing like a good cup of hot chocolate on a cold day. Okay, so let's say I'm here and I'm skiing around this circuit, and there's a buildup of people at this hot chocolate stand, and I cannot get past this hot chocolate stand until the people move. Okay, and so right here at this point there is a slowdown in current. Let's say, you know, Ben owns this hot chocolate stand and his brother Tom is going to open one up too, right along the same path. So there'd be another slowdown here. All right, Tom owns this one. And let's say their sister Sally opens up a hot chocolate shop right here, and there would be another slowdown. Each time you throw a resistor in a series circuit, it's going to slow down the movement of the people, because each time they run into one of these hot chocolate stands, like, oh, that sounds good, maybe I'll buy some hot chocolate. And so it stops the movement of the current. Now, clearly this is not what charge is doing in our wires, but it does kind of give you a more a better sense of what's happening maybe in a circuit. Maybe not. Maybe this is like you're a crazy man. So that's a series circuit. And we said as you add more resistors, the current decreases in a series circuit. Let's take a look at what happens in a parallel circuit. Okay, and I'm going to use the same analogy where basically we have skiers. Here's a battery. Here's the ski lift. We have skiers, and if you were to put this guy in parallel, what's going to end up happening is the hot chocolate stands will be opened up in the middle, okay? And so what ends up happening is, let's say I'm here and I'm skiing around, they're going this way, and let's say the line at this stand right here is pretty long. Well, I might say I'm gonna keep going, and maybe I'll check out the line at this stand over here, okay? So what I've just done is I've now opened up two paths to get back to the ski lift to then repeat the course once again. So by adding resistors, the current is actually increased. Let's say I'm going to open another hot chocolate stand right here, all right? Now I have a third path that I could take. Let's say the line's really long at both here and here. I can now take this path to then get back to the ski lift. Or let's say I open up a fourth hot chocolate stand. Now I have a fourth path in which I can take to get back to the battery. So each time I add a resistor, so that's supposed to be a resistor, add a resistor, the current will basically increase because I'm giving it more choices to basically flow around the circuit. Whereas in a series circuit, all that happens every time you put another resistor in is it just slows the movement down. Okay, it's just another like clog in the path of the electricity. So hopefully that helps maybe make this make a little bit more sense, but maybe not. So just one example for today. I have two electric circuits diagrammed below. Okay, I have diagram A and diagram B. For each circuit, indicate which two devices are connected in series and which two devices are connected in parallel. All right, so let's take a look at diagram A first. Here's a hunk of batteries, okay, and basically currents flowing around this circuit in this direction, we'll say clockwise, okay. So the first thing that the current's going to run into is an ammeter, okay. As the current hits this ammeter, is there any other path for the current to go besides through the ammeter? And I'm looking, and I do not see any other path for it to go. So I'm thinking this ammeter is wired in series, because as I have to go through it, I must go through this ammeter. There is no other way to go around it. So I go through that, and then I hit this resistor. And is there any other way to go besides going through this resistor? And the answer is no. And so it looks like both of these guys are wired in series. Okay, there is no other way around them. You must go through them. Now I come to this junction here, and the current can take one of two directions. It could go to the speaker and then down and then back to the battery, or it could go to the light bulb, down, and then back to the battery. These guys are wired in parallel. Okay, they are wired in parallel. Basically, the current has multiple options for getting back to the battery. Okay, and that's basically the definition of a series versus a parallel circuit. Let's take a look at this one right here. As the current flows around, it hits the speaker. Is there any choice but to go through the speaker? And the answer is no. Okay, so I must go through the speaker, and I'm going to must go through this ammeter because there is no other choice to go around it. So this guy and this guy are wired in series, whereas as the current comes to this junction, basically there's two paths that the current can go. It can go through the light bulb, or it can go through a resistor. And so since there is more than one path for the current to flow through, these two are wired in parallel. Okay, so I hope that gives you a little bit of a grounding and intuition of maybe how series and parallel circuits work. We're going to do a lot more with them, but that takes care of this video. I will see you guys next time.